Hi everybody. In this next video, I want to take a look at the Bohr model, which is using quantum mechanics to describe atomic structure. The first thing I need you to know is it's not perfect. We're actually going to get a better model in a later video, but it does really good for energy. What we get in the Bohr model will work going forward. And because it's quantum mechanics, it has three principles built into it: wave-particle duality, quantization of energy, and uncertainty. Let's take a look at the model and figure out what we can and cannot learn from it. The first thing we need to know is that Rutherford had a nuclear model of the atom that predates this a little bit, where they did an experiment with some gold foil and they saw that because of that they could conclude that the nucleus at the center, which contained protons and neutrons, was separate from the electrons. The electrons were somewhere else, and this was called the nuclear model of the atom. That's what Rutherford could do. He had figured that out more or less. Most of the mass was in the center. In a neutral atom, we also want to remember that number of electrons equals number of protons. And then lastly, the last thing that Rutherford couldn't do was say, where are these electrons? This is what we need quantum mechanics to do, and Bohr took a first pass with the model that you're going to see. What we had to tie it to was data that we had about the atom. And this is what's called the emission spectrum of hydrogen. So you notice this pattern here of lines, and we'll get to this in a second, but I want you to know that there's a term that I'm going to be using called spectrum, which is singular. So there's one spectrum, and then there's many, so plural is spectra. So make sure that you get that vocabulary in your head. And what I want you to see is that there's lines, right? Line, 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 blank space. So they're made up of lines and blank spaces. And in fact, the sidebar of my PowerPoint here is the way the visible part, this part of the spectrum looks. There's a red line, an orange line, a yellow line, so on. And every region has a different set of lines. So there's a set of lines in the visible. There's a set of lines in the IR. There's a set of lines in the UV. And each of those were named for a person, right? They were named for Lyman and Balmer and Paschen. But because we know E equals h nu, right? Quantum mechanics says because energy is quantized, these lines are what we call allowed transitions between energy levels. I can skip between these energy levels, but there isn't anything in between, so I don't get lines. What we needed to do was describe this behavior. Before Bohr ever came along with this model, a guy named Johannes Rydberg had a mathematical equation that described this. It's called an empirical equation. It worked, but he didn't know why. And that empirical equation said that if I wanted to know the wavelength of a spectral line. So if I wanted to know that this was 434 nanometers or 656.3 nanometers, I'd put that here. And I would put it in meters, okay? I would also need a constant. It's called Rydberg's constant. RH. And there are many, many different ways to do RH. It could be in joules. It could be in what is called centimeters to the -1. It could be in what's called meters to the -1. Because I want you to do your wavelengths in meters, Rydberg's constant will be in meters to the -1. And I would give you that number. Please do not memorize that. That's a waste of your brain space. N1 and N2, they're both integers. They could be 1, 2, 3, etc. But they're not the same, right? N1 and N2 are not the same. And they represent transitions. So Rydberg says somewhere in here is N = 1 and N = 2. And lambda well actually 1 over lambda according to his equation, is the space between them. That's all that this equation is saying, is that if I plug in the right ends and the Rydberg constant, I can say where my lines are. So Bohr comes along and he says, this is a really interesting finding, but I need to try and explain it. And so the way that he explained Rydberg's equation was that electrons existed in what he called orbits. So you see this picture at the left, right? This Bohr model of the hydrogen atom. Here's my nucleus and here's my electron. And it looks like the electron is like a planet and the nucleus is like the sun, right? Those orbits are fixed distance from the nucleus. So there's an orbit here, etc. And orbits have, there's that word again, quantized energy. Orbits have energies that they can and cannot have. And another name for these is stationary states. And what he said was, I'm going to define what's called a quantum number. And that describes how far away I am from the nucleus. So it describes the distance. So the one closest to the nucleus is called n equals 1. The next one is called n equals 2. And the third one is called n equals 3, etc. They just keep getting farther and farther away. The bigger the n, the farther away this electron is. So far, so good, right? Because Rydberg had an n in his equation. Bohr noticed and he said that, well, Rydberg showed that the lines were unequally spaced. There's a lot bigger gap between this red and this blue than these two versions of blue, and the gaps just keep getting smaller and smaller. Well, light is absorbed by an electron. And by the way, this right here represents light, and sometimes the letters we use for that are h nu. And then when electrons absorb light, they go from the ground state, which is the lowest energy state, and they go up somewhere else. And up is called the excited state. Anything above the ground, right, these are all excited states, right? Ground state is n equals 1. Excited state is n is not 1. As long as n is greater than 1, we're good. So absorption of light is promoting. The next thing is that light is emitted when electrons fall back to the ground state. So when I start in 3 and go back to 1, that's an emission of light. That's giving off light. Transitions, again, come from absorbing light and going up or down the energy levels, so from one lower orbit to one higher orbit. Let's think about higher energies. And higher energy, just so you know, sorry about that. So higher energy means larger gap. So I just want to look at this on our pictures. Here's n equals 1, here's n equals 2, n 3, n 4. So if I go from 1 to 2 versus 1 to 3 versus 1 to 4, does it make sense that n equals 4 has the largest gap, right? Think of that planet model in your head. Larger gaps are larger energies. Longest wavelength, ooh, let's be careful here. Let's remember our equations. Energy equals hc over lambda. And remember, this is all energies here. So 1, 2, 3, 4, and 5 is somewhere out here. Well, we know from our last one that n equals 5 to n equals 1 from our last principle that this would have the largest energy. Well, let's remember our relationship. If energy is large, lambda is small. I want the longest wavelength, so that's not going to help, right? Instead, I want the lowest energy, right? Longest wavelength equals lowest energy. Let's put some numbers on these now. Remember, let's use that Rydberg equation. It is on a previous slide, but it's 1 over lambda equals Rydberg's constant, 1 over lambda, or sorry, n1 squared minus 1 over n2 squared. And RH is 1.0973 times 10 to the 7 meters to the negative 1. So let's use that equation and let's try to solve these problems. Pause the video and try to work them. I'm going to give you the answers only, so if you're having difficulty getting to the answers that I post when you come back from pausing, then please get in touch, right? Post on the discussion board, check in with me. Let's make sure that you can use these equations. But you need to figure out how to get there on your own with me not telling you step by step. I know that seems uncomfortable, but it's better for all of us. So pause, check the video, and see if you can get to these answers. All right, let's check our answers. And the answer should be a lambda of 4.34 times 10 to the negative 7 meters for the first problem. In other words, 434 nanometers. Or 1.94 times 10 to the negative 18 joules for the second energy. Or the third energy, ionizing, 2.18 times 10 to the negative 18 joules. Again, if you're having trouble getting to those answers, come and check in with me. I can help make sure that you're getting all the variables in the right place, and we can get all your mistakes sorted out before we go on to other parts of the course. I'll see you later.